Okay, and the last thing to do is Laplace's equation. So again, here's our update formula for second derivative. The grid for Laplace's equation, again, this is in some kind of a space. And we have our grid. But Laplace's equation is uxx plus uyy equals 0. And so this is my y coordinate, and this is my x coordinate. So a point here is uij, and then what we want is the value of u here in terms of these. And I think of Laplace's equation as being a steady state heat equation, right? So we want to know the temperature here in terms of the boundary temperatures. So in terms of our grid, that means we have uij is the point in the center. If we increase I by 1, we have j plus 1, that's this point. And we have ui minus 1, comma j, that's this point. And then ui plus 1, comma j, that's that point. And then finally, we have u sub I, j minus 1, and that's that point. And so what we want to know is what's ui sub j in terms of all the other things. So uxx plus uyy equals 0 is our equation. This is our approximation for a second derivative. So that means we want u. Now, delta x is left and right, so this changes in I. So ui minus 1, comma j, minus 2 u sub ij, plus ui plus 1, comma j, all over delta x squared, plus ui, and we'll go j plus 1, minus 2 uij, plus ui, comma j minus 1 over delta y squared equals 0. Right? So the second derivative is always a point for x, is a point to the left, minus twice the point in the middle. Oh, that should be a plus a point to the right. So the point to the left minus twice the point in the middle plus the point to the right. For y, it's going to be the point above or the point below minus twice the point in the middle plus the point above. And what we want is to solve this for uij. We want to solve for these terms. So let's move everything that doesn't have the uij over to the right. So actually, the first thing I'm going to do is just multiply through by. Now let's just move everything that does have a uij over to the right. So we got ui minus 1, comma j, plus ui plus 1, comma j, over delta x squared. That's this term and this term, plus ui j plus 1, plus ui j minus 1 over delta y squared. That's this term, and this term is going to equal 2uij over delta x squared plus 2uij over delta y squared. Great. So having done that, we're going to multiply through both sides by delta x squared times delta y squared, and that will get rid of all my denominators. And that gives me delta y squared times the quantity ui minus 1, comma j, plus ui plus 1 comma j plus delta x squared ui j plus 1 plus ui j minus 1 equals 2 u sub ij, and then I'll have a delta x squared plus delta y squared. That's in bigger parentheses. So when I multiply the right side by delta x squared times delta y squared, this gets canceled out, but it leaves behind a delta y squared, and then I move to delta x squared. We get that. Okay, so finally we get u sub ij by dividing through. So we get delta y quantity squared over 2 delta x squared plus delta y squared times this term, ui minus 1 comma j plus ui plus 1 comma j plus delta x squared over 2 delta x squared plus delta y squared times this term, which is ui, that's parentheses, delta x squared, ui j plus 1 plus ui j minus 1. There we go. So, okay, what we'd like to do actually to make our life a little bit easier is make our grid equally spaced in the y direction and the x direction. So simplify by setting delta x equal to delta y. What that means is that these coefficients here and here just become 1/4. So it becomes uij equals 1/4 ui minus 1 comma j plus ui plus 1 comma j plus ui j plus 1 plus ui j minus 1. This here is the average of the temperatures at surrounding points. Remember that uij is sitting in the center. There's uij, and there's 4 points around it. And the temperatures of those 4 points are these. And we want the temperature in the middle to be the average of those 4 temperatures. So, excellent. We can also write this as, which will become useful in a minute, 4uij equals ui minus 1, the point to the left, plus the temperature at the point to the right, I plus 1 comma j, plus the temperature just above, which is j plus 1, plus the temperature just below, j minus 1. And so that gives us our setting. So then the question becomes, how do you actually figure out what that point, what that is? And so I'm going to set up a particular case. I'm going to have a L-shaped block like this, right? And this is my boundary, and I want to know what's the temperature inside. So I'm going to block this out into it's a 5x5 grid. 1, 2, 3, 4, 5. Yep. 1, 2, 3, 4, 5, and then through the middle will be 5. And then along the top there'll be 5, and then we'll have 3 and 3. So there's my grid. So this is U00 here at the bottom, and that corresponds to this point. And then I've split this up 1, 2, 3, 4, 5, like that. So this is U 0, U1, 0, because it's X is the first coordinate, U1, 0, U2, 0, U3, 0, U4, 0, like that. All of these, and we'll put little X's on them, those are on the boundary. So I know those points, they're on the boundary because that's the boundary condition. For this next row, this point is U01, X coordinate of 0, Y coordinate of 1, U11, U12, U1, U01, U11, U2, 1, U3, 1, and U4, 1. And this is U02, and then U12, U22, U32, and then U42. First number should be X and second number should be Y. So this would be U03, U13, and U23. And this would be U04, U14, and U01, U01, U1, oh my gosh, U04, U14, U24. Great. And these are all boundary conditions because this is all the boundary of my shape. So everywhere there's an X, I know what the temperature is because it's the boundary conditions and we have the boundary conditions stated. And so the rest of my grid is like that. So I've divided this L-shaped up into a grid. And then these are the 5 things that I don't know. Right, so I want to be able to figure out what these are. So what is U11? So for U11, that's this point, is going to be the average of the 4 temperatures around it. So since I multiply both sides by 4, we just sum all the things around it. U01 plus U10, those are the 2 boundary conditions, plus U12 plus U21. So that's what U11 is. What about for U12? Well, that's this point up here. And what's that going to be? Well, it'll be the average of the 4 around it. So that'll be U02, which is a boundary point, plus U22, which is a boundary point, plus U11, which we don't know, that's actually up in this equation, and plus U13. Et cetera, et cetera, et cetera. But what we're getting here is five equations, linear equations in 5 unknowns. Right, my unknowns are U11, U12, U13, U21, and U31. So 5 equations and 5 unknowns. And then there's a bunch of numbers that come from the boundary conditions. So it's a matrix equation, right? You get the matrix of coefficients. X here, a vector, is these 5 unknowns. And then B is all the numbers that come from the initial conditions. We move those over to the other side of the equation. And so the unknown stuff we want is the inverse of the matrix times B, right? And so we can do that. That gives you an answer, but on the other hand, if M is large, I mean, if you got 5 equations and 5 unknowns, that's not a big deal. If you have 5 million equations and 5 million unknowns, getting a computer to do the matrix inverse is really kind of unpleasant. So what we'll do instead is an iterative scheme. where we'll set up a column for our 5 unknowns, which are, let's see, U11, U12, U13. Right, if you ever done Newton's method, this is going to be similar, U21, U31. And we have the boundary conditions. And so for each one of these, right, we start with a guess or an initial condition. Suppose it's all zeros. You could take the average of the boundary conditions. You could take all sorts of things. Just don't pick numbers that are completely away from any of the numbers in the problem. So, and then update, right? Once you have the guess, you know that U11 will be 1/4 the thing to the left plus the thing to the right plus the thing below plus the thing above, right? This is a boundary condition, so you know that number. This is a boundary condition, so you know that number. U21, you took it as a guess and you plugged it in there. U12, you took the guess there, so you plugged that in there. So you've got all those numbers. You can calculate the new number for U11. And then you can do the same thing for U12. U12 is going to be 1/4 the thing to its left, which is U02, plus the thing to the right, which is U22, plus the thing below it, which is U11, plus the thing above it, which is U13. Okay, so U02 is a boundary condition. U22 is also a boundary condition. U11, you've got your guess for it there, and U13, you've got your guess for it there. So you can calculate this. So this is called Jacobi iteration. And one can show that this will actually converge as long as your initial guess is not ridiculously hard, ridiculously off. A version of this is saying, well, U11, the Jacobi iteration says use the guess that you started with, but the Gauss-Seidel iteration says, well, you know, you calculated a new value of U11, so use that new value of U11. And this is a little bit faster than Jacobi iteration. And they give you the right answers. It just, you know, you have to grind through it a little bit. So let's look at the numerical analysis Excel spreadsheet. So here it is. Here's my L shape. And I guess actually I've switched my numbers from, I had this is U13, U12, and this is U21, U23, but it's okay. So this is my boundary conditions. That's the temperatures on the boundary of my L-shaped piece. And I want to know what these things are. And so what we have is 4 times U11 is U21 plus U12, and then minus 50, right? Minus 100 plus 50. So this is the equation. U11, 4U11 equals this. 4U12 is U11 plus U13 minus 200. That's that. U13 is U12 plus 500 minus 200. So that's plus 300. U21, that's this point here. The average of that is this plus this, which is minus 50 plus U31 plus U11. And then 4U31 is equal to 100 minus 100 plus 50. So that's the plus 50, and then plus U21. So we can turn these into equations, right? This equation is 4 times U11 minus 1 U21 minus a U12, and we move the 50 over to the other side, and that should be actually equal to, no, we move these two over to the other side, so that'd be equal to minus 50. So all these numbers that come from the boundary conditions show up here. That's our vector B. If we're thinking about mx plus b, here's our matrix of coefficients. It's called a diagonally dominant matrix, which means that the largest number in each row and column is the number on the main diagonal. And the way we set these numbers up is that, you know, this always happens when we do this kind of an approximation. And these, you can show that these kind of matrices always have inverses. So how do we use Excel to find the inverse of a matrix? Well, we pick a place where we want our inverse matrix to be. That's in there. And then we type in equals MI for matrix inverse, and then you can go down the list just by hitting the down arrow key, and then tab will input that. And it wants an array, so it wants U11, and then you hit shift, and you click down to the other end. And then you remember to close the parentheses. So before we do anything though, you have to be careful with this because we need to apply it to all these cells and think about all these cells at once. So you push down Control Shift with your left hand and then Enter. And it gives you your inverse matrix. A nice trick. So our vectors, U11, U12, U13, U21, U31, they should be equal to this matrix times this column vector. So how do you do matrix multiplication in Excel? Very similar. We take a place where we want our 5 numbers to be, and we go equals MM for matrix multiplication, hit tab, and now it wants 2 arrays. One is the matrix that we're multiplying here, and then hit a comma. Where's my comma? And then we want the second array, which is my vector here. And we close the parentheses. Before we hit anything, you have to be careful. Again, Control Shift with the left hand, Enter with the right hand, and ta-da, you've got your numbers. So we've found the steady state temperatures for, at least approximation for that, for this shape, right? U11 should be about -26 because it's cold there. U21 should be about -17, cold there, cold at U11 as well. U31 should be about 8.21, a little bit warmer. U12 should be -40, and U13 should be about 65 because it's sitting next to this very hot spot, which is 500. Great, so how do we get a picture of that? Well, here's our data. Microsoft Excel does not have a huge desire to do things that are not rectangles, so I just put in 4 zeros up here on the right, and we can click on our data, and we can go to Insert, Recommended Charts, and we don't want clustered column charts, we want a surface chart. And there's our surface chart. Great. So let me scroll over to the right a little bit, and we can do some 3D rotation there. So what have we got here? This is, well, that's that 500, right? So this square part here, that's these zeros. There's that 500, that very hot spot. Goes down like that to -100 on either side. Temperatures, blue is -100 to 0. This orangey stuff is 0 to 100. And then gray, yellow, blue, and green are temperatures climbing up to 500. Yeah, so there's our surface that depicts our temperature distribution. I guess it's inverted a little bit from what that should be, because this area here is that flat part, and then there's the top. And so it's cold in here. That would probably be at -40 point. That's right about there. And then you can see the rest of it. And if you rotate it 180 degrees, Right, now this is looking at it from, there's our peak here on the left, the flat spot is over there, and then there's a call, this is sort of reversed from that. So there's that picture. So again, you can see that if you had lots and lots and lots of rows and columns, finding the inverse would be kind of a pain. So you can take this same data now and you can look at these things, right? This is just the data, the same formulas that we had over here for U11, U12, U13, U21, U31, but we just started with a guess that they were all 0, and then we just iterate a bunch of times, and it eventually settles down to the same numbers that we got previously. And the Laplace Gauss-Seidel, if you look at this one, for example, U12 depends on U11 and U13. So we use our updated value of U11 as well as U13 to get its value. When we go to look at U13, we use the updated value of U12 to get the value there. And the value of the Gauss-Seidel one, if you look at about that, this row is about where it settles down. Nope, one more. Right, and everything then is the same down. So that took 12 steps. The Laplace Jacobi, before it starts settling down, 23. It hadn't even quite settled down. So if we want to continue this, we can go pick a square, pick a cell, pick another cell, hit Control D, goes down. Yeah, and so that doesn't settle down until 24. So the Gauss-Seidel is a little bit faster. So that is some little bit of numerical analysis of PDEs. And you can do all sorts of, you know, with the Laplace thing, you can do all sorts of weird shapes and get pictures of what the solutions would be like. We can't analytically solve for this shape. Well, we could, but it would be difficult because it's not a rectangle. So we can have all sorts of things. And then you can also put, you know, sinks inside of, you can have a shape with sinks inside and stuff like that. So, and that is numerical analysis.